Okay, this is in a new talk in the virtual seminar on geometry with symmetries. In this occasion, I have the pleasure to introduce Mariel Sáez. She's a professor in Pontificia Universidad Católica de Chile. And she will talk about translating solution to mean curvature flow.
Well, thank you very much for the invitation. And I was telling Emilio before starting that I will start the first part with more like a survey talk, and at the end I'm gonna get into some new results. But I mean, if I'm going too slow, you can interrupt me and I can speed up if you want, or the other way around, of course. So I want to start by sort of introducing what is mean curvature flow and what do we mean by translating solutions. And since this is a seminar mostly on Lie group actions, I'm gonna get the Lie group at like halfway of this talk. You're gonna see a Lie group. But at the beginning, it's gonna be everything in Rn, which I guess is kind of a boring Lie group, but still I guess counts somehow. So the mean curvature flow arises as the gradient flow of the area functional. And that means that if you have a surface, what's going on? Give me 1 second. The pen is not pairing. One minute. So as I was saying, so you have a surface M, and then you compute the area of this surface M. And if you take the first variation of that, so if you take M plus T times some variation of that, what you're gonna get when you take the derivative of the area is the mean curvature vector times V, the mu, where V here is the phi. No, the way I wrote it, I mean, sorry. Let me write it like this. Like this is the phi T. So minimal surfaces are surfaces that H is equal to 0. This is minimal. So critical points of the area functional. And the mean curvature flow is the steepest descent of area. So this, I'm not writing well this of area. So basically, what you want to do to decrease this the fastest is take, if you think about M parameterized by X, you want the XCT in the normal direction to be, yeah, okay, this is not the best way. Let me write it like this. This is if X is co-dimension 1. It can be in any manifold, but let me do it for now in R plus 1. We're gonna change manifolds soon. In this case, there's only one normal direction, because if I take any codimension, then this doesn't make sense in the sense that you have many normal directions. So let me write it like this. And yeah, so let me put an extra page here. So you can study this from the PDE point of view. Can be studied as a PDE. And when you study this as a PDE, minimal surfaces are elliptic PDEs. And mean curvature flow is sort of the parabolic version of the minimal surface equation. So mean curvature flow is parabolic PDE. It's degenerate. And let me show you one example so we can sort of be in the same page about how this is degenerate. So for example, if you have that M is described as a graph, if you can describe it in this way. This is M at time t, and X is in some domain omega. In general, you're gonna need this omega to be, I don't know, either it can be Rn, or you can have to put a boundary condition or something. But for now, let's not worry about that. Let's only worry about the mean curvature flow. And in that case, the equation that you get is something that is that looks like this. Right, like this. Sum. Usually we never write the sums, so I'm gonna forget them often. JU. So this is a sum in I and J. And if I had done this more carefully, I would leave more space for the second derivative. So if you kind of ignore this, where is the pointer here? If you kind of ignore this part, the second component of this, I forgot already how to do total line. It seems like if you ignore this part, this is just a heat equation. So when the derivative is kind of small, it's almost like the heat equation. But when the derivative is large, this coefficient is becoming zero. It's becoming at the PDE. So somehow it's an elliptic. I mean, it's a parabolic PDE, so you can use sort of PDE tools to treat it, but at the same time, it's degenerate, and that will imply some things. And for that, I kind of want to give you maybe one of the only examples that I know how to compute. Yeah, no, I think there are like 2 or 3 examples that I know how to compute. But if you take a sphere, for instance, in this case, the mean curvature, and maybe I should have explained more about what the mean curvature is, but the mean curvature is the trace of the second fundamental form. So it's all the principal curvature, is the sum of the principal curvatures for me. And what are the principal curvatures? So principal curvatures. So sorry, if you take let's say the derivative of the normal vector is the trace of that. Is the trace of that. The principal curvatures are the eigenvalues of this matrix, of the matrix of the derivative of the normal, and the H for me is the trace, is just the sum. And geometrically, when you're in a 2-dimensional surface, that means that if you take any curve on the surface, you take the curvature, all those, you take the maximum, minimum, and those are the principal curvatures. So the eigenvalues in this case are the maximum of the mean and the minimum of that of those possible curvatures. So all this is to say that in this case, the mean curvature is just for me and over the radius of this sphere. So this is, if you try to evolve this by mean curvature flow, this is something that in all directions is gonna have exactly the same speed. And so it's not unreasonable to think that one solution, at least, I mean, we have to discuss if there are many solutions, but at least one solution is gonna be a sphere for all times. And in general, something that I also didn't talk about, you have always 2 choices of normal. You can point out or you can point in. So the choice for this to be parabolic is that when you have something convex, it should be pushing in because you're trying to minimize area. So what you expect is that for all times, you're gonna get a sphere here. So you make the answer that the solution is gonna be a sphere of different radius for all times. The unit normal in this case is omega. That's the one pointing outside. So if you want to go inside, that means when you take the derivative of this in t and you multiply by the normal, that is the same omega, you should get minus n over r. And the derivative of this in t, because the omega is not changing, is just r prime n over r. And this is something that one should be able to solve. But I'm gonna just tell you what the solution is just r at 0 minus 2 and t. So this is a simple example to compute. And the reason why this example is important is because you see several things on this. One thing is that the solution exists, but it stops existing after some time. So you see that square root becomes 0, and that means that the sphere is actually shrinking to a point. So there is a solution, but the solution doesn't exist for all times. And on top of that, because this is a PDE, you have a comparison principle among solutions, which geometrically means that if you have two solutions to mean curvature flow that are smooth solutions and do not touch at the initial time, then they will not touch during the evolution. In particular, if you have any compact initial condition, if you have any compact surface, let's say, blue is not a good choice, I guess, here. If you have anything that is compact, green I think is a bit better, then you can draw, I mean, you can enclose that in a large sphere. And if these two things are not going to touch and the one outside is going to shrink to a point, that means that the evolution inside cannot exist for a time that is longer than the thing that's enclosing it. So that means that all evolutions are going to develop some sort of singular behavior. And one of the main things that you want to understand in mean curvature flow is how is that singular behavior. Okay, so all this is to say that, yeah, that wasn't better. All this to say that somehow a lot of the work in mean curvature flow is to try to understand how are singularities in the evolution. I mean, this is what we do a lot in mean curvature flow. And somehow a lot of what I'm going to say is sort of towards the idea of understanding certain type of singularities. So one thing that you could think with this example is that maybe everything behaves as a sphere and shrinks to a point. And this was one of the things that people asked themselves when this was at the beginning of the times, let's say. And for embedded curves, this is actually the case. Everything sort of becomes convex and then round and shrinks like a sphere. But then if you know that and you know how to compute explicit things, actually one explicit computation that I also can do, but it's sort of the same computation. If you have a cylinder, this is gonna shrink like a sphere, and you can see that this is gonna shrink actually to a line and not to a point. So you already see with this example that it's non-compact, so it's not exactly the setting that we had before, but that you can have singularities that are not points, but lines in this case, or like a higher dimensional thing. And when they were still sort of trying to understand examples, like one of the most famous examples is this dumbbell sort of initial shape in which the sides shrink like spheres and the neck shrinks like a cylinder. So question here is what goes faster, right? I mean, is this gonna shrink like to a point or more like to a line in that region? And the answer actually is that more or less anything can happen depending on how you balance the different things. You could have that actually this becomes convex. This is one option and shrinks to a point if the neck is very small compared to the sides. So you could have that this is evolving like a sphere, but you can also have that this sort of develops a pinching there. And in a non-generic case, in a more degenerate case, you can even have that one side shrinks and the other one doesn't. So you'd still develop a singularity, but it's just like one point sort of on a side. So you can have many different types of singularities, even with this example. Well, many, like 3 different types of singularity, even with one simple example. So the question back then was, I mean, how we characterize singularities? What can we say about all these singular behaviors? And one possible way of classifying singularities again, this is sort of a choice somehow. Let me see. So how do we study singularities? Or how?
Mariel,
Yeah.
I have a general question.
Yes.
When you talk about convergence, in which
Yeah.
sense? Is there a precise way or about how sort of sense?
You mean these to that kind of singular behavior? These are smooth embeddings in Rn in this case. I'm just still talking in Rn. So this is just a parametrization, right? And the parametrization in all these examples becomes singular at a point. And the way you see that this is singular is that basically that it stops being smooth enough to define curvature. The precise statement here is that the second fundamental form becomes unbounded at those points. So basically the second
another
derivative is not
question.
yeah.
The solution immediately stops when appears one singularity or might.
Okay, yeah, this is a question and it's not, it doesn't have a precise answer in the following sense. I mean, one of the things that you want to do after you understand singularities is how you continue after the singularities. And for that, there are different approaches, I guess, depending on what you want to do with that solution. So you can define the solution past the singularity, but there are different ways of doing that, and they all have their issues. I mean, and this is kind of a very large topic somehow, and different things that you can do. And actually, maybe let me say a word more about that when I describe this rescaling procedure. But somehow, in this particular case of the dumbbell, you could do something like in the Perelman sort of setting, you know, like you can do surgery and you can just cut this bad point and continue the flow. And then you have two spheres, two separate spheres that are going to continue. But then you have the same issues that you have in Ricci flow, that somehow you have to make sure that when you cut, you're not producing new singularities. You want to understand how is the piece that you're cutting, that you have a finite number of singularities, exactly the same issues. You can do sort of exactly the same idea, and you have exactly the same issues. And this has been done in some cases. In general, it's not known as generally as in Ricci flow for 3 dimensions, but at least in the mean convex case, when the mean curvature is positive, then you can do exactly, you can follow exactly the Perelman program. And you know how to do it. Are there any other questions up to here? Okay, so one way of studying singularities that is similar to what people do for Ricci flow is to try to see to do rescaling. So the answer here is maybe rescalings. And how you rescale, it depends on how is the singularity. So something that maybe I don't want to talk about in detail, but the second fundamental form, I mean, what in mean curvature people write like this is the sum of the squares of the principal curvatures. And this is sort of a measure of if you're becoming singular or not. And something that one can prove is that if you take capital T being the maximal existence time, this is always bounded below. So, and this is sort of their natural rescaling for this in the parabolic setting. So if you have an upper bound as well, then you say the singularity is type 1. And then when you rescale, what you see is a so after rescaling, say here, you rescale, and you see a homothetically shrinking solution. And actually, I mean, these ones, you already saw two of them. So it could be a sphere or it could be a cylinder, are things that are, this is a cylinder. So are things that you can write as t minus t and some fixed shape. So are things that have this form. At least in most cases, this is what you see. And in the case that the mean curvature is positive to start with, this is preserved, and these are more or less is everything that you see, cylinders and spheres. I mean, could be higher dimensional cylinders, but I mean cylinders. If you don't have this, so if the singularity is not of type 1, the singularity is of type 2. Type 1 or type 2. And then the rescaling is somehow is different and it's less precise. And what you see here when you rescale, this is the rescaling, what you see is what they call an eternal solution. So a solution that is defined for all times. In particular, this cannot be compact because we know that compact things develop singularities in finite time. So this cannot be compact actually, because then it could not exist for all time. So what this means is that exist for all times. A very particular type of eternal solution, but somehow is what you expect to see many cases of in the singular behavior are translating solutions. So finally, I'm coming to explain the title of the talk. So an example of this are translating solutions. And that means that m at time t is given by whatever it was at the initial times plus t times and a translating direction. So it's the same shape that just moves in one fixed direction. And in Rm, because all these things are invariant under rotation, usually we assume that this thing here is just the last coordinate vector, and it's easier if they move down rather than if they move up. But so translating solutions somehow are the simplest example of eternal solution, and they are expected to be in many cases models of singularities, and that's one of the reasons why we study them. I mean, that's one of the main reasons. Also because they're examples of mean curvature flow that are non-compact, and in general in the non-compact world, there are many things that are known, but much less than for compact solutions. So I think another reason is really to understand what kind of things to expect for non-compact evolutions as well. I mean, this is a motivation. So what are examples of this? And I'm gonna show you the other example that I know how to compute, and then I'll show you pictures, because with this more or less I finish everything that I know how to compute. At page here. So the example that I know how to compute is the one-dimensional case, and this is actually the only solution in one dimensions. So if you assume that the solution is translating, and I can write it as a graph, I think I'm gonna write it like this. I'm gonna let it move down. You can do it when it moves up as well. So if this is, because it's one-dimensional, I'm gonna call it gamma of xt. Gamma of t is gonna be just 0 minus 1. The normal vector in this case is gonna be minus gradient u1 divided by the normal of that. and I'm being too generous here because this is just one dimension, so this is just one derivative, the only derivative that I can take. Squared. And then you can compute the curvature of this, and if you do some manipulations here, what you see is basically that you have that u prime prime 1 plus u prime squared. The curvature is some multiple of that. I mean, the scaling is not exactly that. And I think because of the choice I made, I think this is a -1. That matters so much. But this is something that you can integrate, actually. This is if you integrate here, yeah, integrate. On the right-hand side, you get arctan of u prime. And on the left-hand side, you get, so maybe, let me say that I made the correct choice and I got a 1 there. This depends on the sign of the t, of the minus t or plus t there. And you get here an x and some constant that depend on the initial condition. Here I'm centering it, so you have an additional constant here. That when I have a plus or a minus, I think I want to have a minus so it integrates well. That means that u prime is minus the tangent of x. And if you integrate again, that means that u of x is the logarithm of cosine of x. And the plus or minus depends on which direction you want this to translate. So with all those choices, basically you have a solution that looks like this, I think, and is between two planes. I mean, two lines in this case. And it translates, it just moved, keeping the same shape for all times, moves down. And this is usually what people call the Grim Reaper. And this is going to be a relevant example today. That's why I kind of wanted to compute it. So this is something that has exactly the same shape for all times and is just moving downwards. And in one dimension, this is the only translating solution that you can find, actually. This is the only possibility that you have. Okay, so in one dimension we know how to classify solutions. So the question is, what can we say in higher dimensions? And then as I said, this is the only one that I really know how to compute. And then, so for higher dimensions, I just brought pictures. So the first one is our two-dimensional examples in R3. The first one is the same Grim Reaper just cross R, so this is just moving down. So this is explicit. This one, I guess I also know how to compute. But out of this, in one more dimension, you can also tilt the Grim Reaper and get a different one that is generated by one curve that usually people call the tilted Grim Reaper. This is still moving downwards, but it's not anymore just straight curve. It's something that looks like this and still moving in that direction. And this also has an explicit parametrization that I kind of don't want to show you now, but you can explicitly say what it is. And these were like the examples that people knew when they knew the other one, because, you know, like the first one was kind of direct, the second one is less direct, but not so hard to construct. And then people start looking for other things that were easy to compute somehow, or at least to study. And the next step then that people studied were things that are rotationally symmetric, because, you know, then it's something that, again, is a sort of a one-dimensional, I mean, reduces to a one-dimensional problem. And these were classified by Schnur and Schulze Klarerbach. And actually, rotationally symmetric, we have only two. The ball soliton, that is an entire graph, quadratic growth, or, you know, downwards in this case, and something that looks like a catenoid. So these are the only rotationally symmetric ones in R3, in Rn. So, okay, are these all the examples? I think I repeated the examples again. Sorry, I think, okay, so I had one more. So after that, we ran out of one-dimensional examples, and then you need to do something more. And then there is another example that is called the delta wing. That is that one here. This one is called the delta wing. I don't know what I did. I think I changed the size of the pen somehow. So this is called a delta wing. And the difference between this and the Grim Reaper, or how you see these are different, is the width of the band where they're defined. They're all defined on a slab, and depending on how wide is the slab, for small slabs, what you see are Grim Reapers. For big slabs, what you see are these delta wings that are not anymore one-dimensional or symmetric, but still sort of just defined on a slab. And then there is a theorem by Wang. I mean, this is a combination of things, but Spruxiao showed that all these translators are in fact convex, and then convex ones, when they're graphical, they have to be defined either in a slab or in the whole space. You cannot have any other domain of definitions. So in the whole space, you have the ball soliton that you're seeing there on the, I guess, left side of your screen. And graphical on a slab, you see the Grim Reapers and the delta wings. So in fact, people classified all the graphical ones, and all the graphical ones are just the ones that I show you. There are no more. They're all in a slab, or except for the ball soliton that is defined everywhere, and you know very well how it behaves. And there are planes, of course, but these are kind of the non-moving translators. Okay. And we have the rotational ones, and the question is, can you construct more? And then people started like sort of doing constructions, and they found many other examples. I mean, there are many others. There you're seeing 3 examples. The first one is called the trident. The second one, I think, is the second one, I think, is the helicoid, and the, no, not the, yeah, I think this one they called, I forgot the name now. And the one below they call it the Shirkinoid. And these names come from some analogies with minimal surfaces. And one of the main tools that people use here is that, how were these examples found? I'm running out of time. How were the examples found? So I think I'm gonna skip a little bit. So one observation that is very important here is that translators in Rn, translators in Rn+1 are minimal surfaces with respect to the metric and the standard metric. So these I'm thinking about translators are moving in just downwards. I mean, the -x-1, of course, it can be other direction, and you see something similar. But the point is that a lot of the theory is sort of developed in analogy to minimal surface theory, because they are minimal surfaces in that context. And in a minute, I'll say why I'm mentioning this. Okay, so I'm gonna skip a little bit because I'm going slower than I thought I would be, but there are more examples, and actually I kind of wanted to mention some of the examples because I wanted to show the kind of things that the way you're using that these are minimal surfaces, but because a lot of the theorems that you can use, the regularity, the behavior, comes from the fact that these are minimal surfaces in some metrics. But let me go to the point of what I want to say, to see if I can get at least a little bit of what we're doing now. that is, what can we say in other geometries? I mean, can we talk about translators in different geometries? And this is kind of the point of what I wanted to say today. Of course, to talk about particular solutions in very general manifolds is hard because, I mean, somehow we're using to construct these examples a lot of the symmetries. I mean, to see one-dimensional or rotational symmetric is because Rn has those symmetries. So to say something about translators in a very general setting, you can maybe define them, but it will be hard to construct anything because you need to know a little bit about the symmetries. So I guess the first question that I need to answer here is, what do we mean by translators in this context? So basically, as I said before, the main feature of this is that these do not change shapes. So so the idea is here we have a one parameter family of isometries. Family of isometries. And we want M at time t just be defined as this isometry and apply to the initial time. So it's sort of the same shape, and this is just deformed in a very particular way by this. And then when you solve what this means, I mean, what kind of equation this is going to satisfy, you're going to find that the mean curvature is going to have to be equal to whatever metric. So I'm thinking that here I'm in a manifold M with a metric G, let's say. It's gonna be.
Mariel, just a quick question. When you
Yes.
write MT, you are changing only the Riemannian metric or the
I'm changing
differential
embedding.
manifolds?
The metric is also, I mean, you have a fixed ambient manifold and you have an embedding. This is your M0. And what you're changing is the embedding of that manifold, basically. This is what you're doing always in mean curvature flow. So the way you change the embedding for these self-similar solutions is very simple in general. In the case of Rn, you're just moving the manifold. If you're talking about translating, in this case, you have this one parameter isometries in whatever you can find in your space and changing the original embedding. I'm gonna try to give you an example in a minute. Okay, so what was I saying? Let me see what I can, where do I want to go with this? Yeah, so okay, so what you have here is the derivative in T is gonna give you some fixed Killing vector field and a vector, and nu is still the normal vector, and V is C phi dt. And this is gonna be a Killing vector field. So to start with, if you wanna be able to compute particular examples, you have to choose a space where you know something about the Killing vector fields. You need to have some to be able to compute examples of this nature. And one case where these things have been studied are in the Thurston geometries. So what I want to talk about now are examples in Thurston geometries in 3 dimensions. So actually, some of the papers that I'm gonna mention are very recent, so I really don't know them that well. There's one that is like less than a month old, so I haven't really read them so carefully, but I mean, you have examples in hyperbolic space. In H2 cross R. I'm leaving some space because I want to say something about each of them. In nil. in Sol, and a very recent paper that is also in SL2 part. And I wrote the references because otherwise I'm gonna forget, but let me tell you a little bit what people do in these cases. So here you have Grim Reaper type solutions. Rotationally symmetric. You cannot rotate in every dimension, in every direction here, but there's some that you can rotationally symmetric. The reason why they started with this is because these are the ones that are sort of one-dimensional, I guess. I mean, so this is what people would do. You have something similar in the case of H2 cross R. So you also have these types of solutions. In Neil, you have a very complete classification that maybe I'm gonna skip for now because I'm not gonna use them in the last part, and I have very little time. But you also have many different types of solutions here. In SL2, this is a very recent paper, and you also have like some Grim Reaper type kind of solutions. I think the only thing that they do in that paper is Grim Reaper type. And in Sol, and this is the example that I want to focus on now, you have Grim Reaper, but you don't have rotational symmetrics because somehow, I mean, rotational symmetry is not something natural to the metric. So somehow what you expect to have in all of them is Grim Reaper type, maybe, and I'm gonna say a little bit more about that in a minute. And rotational asymmetric, if that's not a symmetry of the space, is harder you're gonna find. So somehow, if your space is more rigid, has less symmetries, you expect to have less translating solutions that have symmetries, but maybe you can have solutions that are not symmetric, and I want to say a word about that. Other thing that people have studied, and I'm gonna try to say a word also at the end, are things that are graphical. Usually the examples that we have are graphical and rotationally symmetric so far, but you could try, as in RN, to construct things like the delta wings that are not symmetric but are graphical. Okay, so in the last, I think, 5-10 minutes, let me tell you what are we interested in. So like the question that I guess I want to address is, how can we unify all these solutions? And actually, when we started looking at this, we said, I mean, what happens? We were sort of inspired by the paper in Sol, but what happens if we take in R3 a metric that is of this form? In fact, hyperbolic space is included here. That is just taking lambda1 equal to lambda2, and that allows you to rotate in among like x, y variables, and that's where you get the rotationally symmetric. If you take lambda1 plus lambda2 being 0, you get Sol. If you take one of them being 0, let's say lambda2, then you get H2 cross R. So somehow all these belong to the same family of metrics. And in some cases, you see similar solutions, and in some cases, you don't see like the rotationally symmetric ones, for instance, when you go to Sol. So, or we don't know at least that they do exist. So the question, I guess, that we are trying to understand is how you unify all these sort of different perspectives, and what kind of solutions can you construct in this case. So what I want to describe in the last 5 minutes is a little bit about how you can go about constructing Grim Reaper solutions, and how we can see all the ones that were constructed before from this construction that I'm gonna describe here. what I'm gonna describe is mostly based on a paper by Pipoli, by Giuseppe Pipoli in the case of Sol, because we sort of are choosing that setup. In the other ones, they're choosing another representations of the metric of the space. But I mean, you can go from one to the other in any case. So what is the idea? So the idea is that all these are generated by one curve. So the first thing that you need to know is what are the Killing vector fields, to see where can you translate vector fields. This is the first question that you need to answer. And then we impose symmetries in a way that the solution is generated by one curve. Yeah, I think I should be finishing, but let me say at least a little bit of what these things are. So the answer to the first question, the Killing vector fields, that you see in this case are these, the derivative in the x direction, the derivative in the y direction, and lambda 1 x e minus lambda 1 z dx. Let me move it down, maybe. I need to put it all here. Plus lambda 2 y minus lambda 2 z, I guess. This set. So you're gonna translate in a linear combination of these vector fields, and you're gonna be invariant in the direction of another linear combination of these vector fields. So let me see what I can manage to say in the 5 minutes that I have. But let me give you one example, maybe. Let me start with one example. So if the translator is F1 invariant, then you can write this as X, Y of S, C of S. And the normalization that we do is that YC is arc length parametrized. And the translating direction. I just want to write one equation here. It's some V that is going to be A F1 plus B F2 plus C F3. In reality, this one you can take always to be 0 because this is a tangential vector, so it just accounts for reparametrizations of the surface. So usually you take all the tangent ones to be 0 because, I mean, you can always reparametrize them out. So you just have these two possible directions. And then out of that, you get a system of equations that says the following. So being arc length means that you can write y prime as cosine of theta e to the lambda 2 z, c prime for some function theta, sine of theta, theta prime is going to satisfy lambda 1 plus lambda 2 cosine of theta minus theta lambda 2. I hope I'm not making a mistake here. This theta is b, sorry. This is b plus c e lambda 2 y cosine of theta. Maybe making a mistake here, but somehow to study E1 invariant solutions, you want to study this system of ODEs. In the case of Sol, this sum is 0, so you have that this term here is not there in that case. But you see some continuity respect to the parameters somehow, to how if you change lambda 1 and lambda 2 continuously, then this system is going to change continuously. And in fact, this is what we can say, and I'm not going to do it. I was planning to compute like minimal case when you take B and C 0, that you can compute explicitly and see how these things change continuously. And you see that for different choices of the parameters, you're gonna basically see the solutions that you have before, and you can sort of unify all the perspective for the Green-Reaper equation. Here, I mean, there are different cases somehow. You have more rigidity. Anything that is sort of invariant in the F3 direction actually are just minimal surfaces. In the case of Sol, and also in the case when lambda 1 and lambda 2 are, I mean, they're not in sort of in the special cases. But something that I think, I mean, two questions that I wanted to sort of discuss, and I don't have much time to discuss, is one thing is that is missing here somehow compared to the perspective in RN, is that we don't have like this characterization as minimal surfaces. In H2 cross R, for instance, you know that there are many minimal surfaces, so it could be kind of interesting to see if you can do a similar setup. There are some partial results if you translate in some particular directions, but not in any direction. And the other thing that I think is kind of interesting to see is that in these geometries that you do have rotational symmetry, you can construct these ones, but maybe because all this seems to be sort of continuous on the parameters, maybe you can have solutions that are not rotationally symmetric in the other cases, but graphical and in some sense close to the rotationally symmetric. So I think it's kind of interesting in the sense that this could give you a way of sort of maybe continuously move from one geometry to the other, changing the parameters somehow of the Lie group action that you have underlying there. And I'm sorry, I didn't plan very well the time, so I think I'm gonna finish here, and I'm just not gonna compute anything else.
Okay, thank you very much, Mariel. Very nice talk. I enjoyed from a very naive point. Are there any questions?
I guess I have a question. So, hello. So my name is Bent Orsted. I'm listening from Denmark. Thank you for a very nice lecture. I'm curious about what your first example was, what we sometimes is called a self-shrinker, right? The sphere is a self-shrinker. And just like looking for translating solutions, we could look for self-shrinkers.
Yes.
And of course, a lot of work has been done in this area, in Euclidean space, and even with different topology. So I'm curious, if we take one of your Thurston geometries, could there be a similar statement that, you know, take a conformally related metric to the standard one, look for minimal surfaces, and look for killing vector fields that are not killing but are conformally killing vectors.
Yeah.
And then in exactly the same way, you know, look for self-shrinkers in your geometries. Could that be done, or is that interesting for you?
Yes, this could be done, and actually in the case of hyperbolic space, it has been partially studied. Also, like very simple examples, you know, like one-dimensional, like But yes, this is actually something that is of interest, and it has been sort of in some cases sort of proposed. something that I didn't mention here that also has been studied, and also they have thought about these examples when you have metrics that are cross products. So you have sort of M cross R. In the case of translators, the R is the translating direction, and the M is the one that has the symmetries. But you can do sort of a similar idea for other type of conformal. This is something that is sort of there, but I think it has not been as developed as the translators so far.
Mm-hmm. Let's see. Okay. Well, thank you. Yes.
There's a lot of room for that still.
Mm-hmm. Yeah.
Hi, this is Matt Grayson. I noticed you omitted the three-sphere in your geometries.
I did.
Is that, I assume that was deliberate.
It was, yeah.
I have many examples, some of them breathers, periodic. They translate in time and space. So I would be happy to send such examples, or maybe you want to avoid the three-sphere altogether.
No, I thought about including them, but these are slightly different. So because I was running out of time, I kind of decided to not mention them. But yes, if you can send them, that would be actually great, because I know about them, but I haven't really, I don't know how to put them together with this yet.
Okay, fair enough.
Yeah, but no, thank you. That would be actually great, actually, to see, because I know, this is kind of a very different geometry somehow, right? Different examples.
Yes.
Okay, are there more comments or questions? Okay, if not, we thank Mariel again. Thank you very much, Mariel.
Thank you.
Very nice. Thank you.
No, thank you. Thank you very much for coming, actually. I'm happy to finally meet you, actually. I usually cite your work.
It's okay.